All right, so tonight we're going to begin talking about a very exciting topic in the world of data science, and that is neural networks. This has become sort of a buzzword lately. You'll see it everywhere, but it's something that you really need to know how to use. It's an important tool. And so tonight's going to be kind of an introduction to it. You're definitely not going to walk away tonight an expert on the topic, but this will hopefully at least ease you into some of the concepts and kind of show you how to work with it in Python. So one of the best ways to start explaining neural networks is to compare it to basically how our brains work. I'm not a biologist, so I probably will botch this explanation, but I have this nice picture to help me. So basically in your brain cells, they look like this here. They have dendrites, which are these like tentacly things. And you can think of these as like inputs, so like features in a data set. And then you have the nucleus, which is kind of like the brain of it. And then you have an axon that has like impulses travel down it, and then to these terminals. And so basically, some of these get activated if it's a strong enough response, whereas others do not get activated. And so that's kind of how a neural network works. So this here below is basically one neuron in a neural network. So you have a bunch of inputs, which are basically features. And then you have the neuron, and then it has an output. And you'll notice there's a bias here. You can think of the bias like in linear regression as kind of an intercept term. And then this next graph, this is kind of more in depth of what a neural network looks like. So you have your input layer, so again, the features. Then you have what's called a hidden layer. So the hidden layer is made up of any number of neurons. Each one of these circles is one neuron. You basically could have any number. You could have a single one, you could have 100 of them. But basically, each of the inputs, you can see here if I get my pen, so each input connects to each neuron. And each of these lines what represents a weight, which if we're talking about linear regression, that would be like the coefficient. So basically how much of that input goes into this neuron in the hidden layer. And then basically, depending on what input we get multiplied by the weights, we then pass that through what's known as an activation function. And this basically adjusts the value that you get in this hidden layer neuron. And it can do a lot of different things. So it can squash it between -1 and 1. It can squash it between 0 and 1. And it basically allows the neural network to turn off or on these different neurons depending on your input. And then you can actually have multiple hidden layers. So we could have another hidden layer here with another set of neurons, more or less. And each of the neurons in this first hidden layer would basically be the inputs to the next hidden layer. And you can have multiple hidden layers actually. But once you get towards the end, then you're going to have your output layer. So this is whatever you're trying to predict. So it could be a singular value if you're doing kind of a regression task, or it could be multiple different outputs if you're doing like a classification. So that's kind of an overview of how, yeah, sure.
So if you can have multiple hidden layers, does that mean you're also going to have multiple activation functions?
Yeah, well, so each hidden layer can have its own activation function. Okay. So usually you'll have kind of the same one, but you could have different ones for each, yeah.
Okay. So something has to happen in that hidden layer. It's
right.
Not just numbers passing through like water under a bridge. Things actually are transforming.
Right, yep.
Okay.
And we'll go through the activation functions here a little bit later. But let's see, before we get to this next part where we kind of manually make a neural network, I wanted to point out this YouTube video / like channel. It's 3 Blue 1 Brown. You've probably seen it before, but their whole series on neural networks is amazing. He explains it in a really intuitive way, a much better way than I can. So I definitely would recommend watching all the videos he has in this too to help you out. I'll go ahead and just put the link here in the chat. And in the video, he actually uses this digit recognition data set that we're going to use tonight in the activity. So it'll be super familiar too. So definitely check that out. All right, so now we're going to first try to kind of make one manually in Python. You'll never actually do this because there's a couple really good libraries to do it for you, but this might help you understand kind of the math behind how they work. So to start off, we're going to make some fake data basically. So our input data here, these would basically be features. So we have 3 columns and it's basically binary features. So it's either a 0 or a 1, just to keep it simple. And then we have our targets, or they're called labels here. So we basically have 2 different classes we're predicting between. And then this last part just kind of reshapes this so that it's in a array shape that we can use with NumPy. All right, so we're going to set a random seed for NumPy just because we're generating some random numbers here. And so we're going to create 3 weight variables for each of our features we have, and it's going to be randomized. So they're going to start off somewhere between 0 and 1, just randomly, and then as we train, those will kind of move in either direction to create basically a better fit. This, you'll realize, is a lot like linear and logistic regression. It uses gradient descent almost the same way. You just have a lot more steps, and it's a lot more complicated when you have multiple hidden layers, which we'll get to in a second. But then we're also going to create a bias term for our one neuron. Again, this is kind of like an intercept term. It's just kind of a flat value that's added. But we'll also randomize that. And then LR is learning rate. So when we do gradient descent, we need a learning rate so that it kind of learns slowly and gradually, and it doesn't overshoot the minimum or maximum. All right, and then this one, run that cell. And then we need 2 helper functions. So you'll remember we used sigmoid before for logistic regression. Sigmoid is actually an activation function. It puts numbers between 0 and 1. So it can be really good for binary classification when you have just 0 and 1 as your classes. And then since we're doing gradient descent on that, we need the derivative of that sigmoid function in order to perform gradient descent on it. So this is basically the derivative of the sigmoid function. So we'll just run those and have those to use. Now this is going to be our training. So I basically am just creating an empty list of the weights and biases and our mean squared error so that we can plot it later. But so basically each time you train your neural network and it basically goes through the hidden layers and goes to the output and calculates its error and then adjusts the weights, that's one epoch. And so you usually run it for multiple epochs so that each time, you know, it learns a little bit more and eventually it learns enough that it can correctly predict your output. So at the beginning of the loop, we're just going to append the current weight for each of our 3 weights and then the bias. And then we're going to grab our input data as the input. And so the first step is to kind of go from left to right in the network. That's known as feed forward. And so this is basically just multiplying the inputs by the weights and then adding the biases. And then this Z is basically passing that through our activation function. And so now we're about at the output. So we basically compare what we got from our neural network to what our true values are here. And this is kind of just the absolute error. And then we'll print that out each time just to see how the total error changes. And then we're also going to use mean squared error and kind of measure that as we're training. So then the next part is basically working from the right side of the network back towards the beginning. So it's basically adjusting those weights and biases depending on how close we were to the true output after doing the feed forward step. So this uses the derivative of the cost function and the derivative of our predictions, which are here. And then we basically multiply those together. And then we do a little bit of matrix math using the transpose of input data so that we can do the dot product down here. And this basically gives us our updates to our weights. So we have the dot product of our inputs and then our basically our change in slope for gradient descent. And then we multiply that by our learning rate so that we're just moving a little bit closer towards the right weights and biases and not too much so that we don't overshoot them. And then this last part basically adjusts the bias with each epoch. So we'll go ahead and run this. This will run for 1,000 epochs. It'll do it pretty quickly because this is really small. And what you're seeing printed out is the total error. So you can see that over time, it gets less and less. And eventually it kind of slows down. So like it's not getting that much better as we go along. The improvement kind of slows. And that's kind of always true for neural networks and just for gradient descent. Eventually your improvements just kind of level off. So we see we decrease the error quite a bit after 1,000. We started at 2, and we got all the way down to 0.05. All right, so now we can plot all these weights and biases and mean squared error to kind of see how they changed through the training. So we can see weight 1 actually started off here and went down a little bit, but then it increased. We can see weight 2 basically increased the whole time. Weight 3 decreased. And then let's see, this is the bias term, basically decreased the whole time. And then our mean squared error, this is what we should see. It decreases dramatically at first, and then it kind of levels off as it gets lower and lower. So that's kind of what you'll usually see. You don't usually print out the changes in like the weights and bias terms, but you can always print out how your accuracy metric changes or your loss function. And so you'll want to do that as we use them with the Keras library here in a second. But then this next part will show us how to do predictions. So let's say we have a new data point. Remember, we have 3 features, 0 or 1 for each of them. So this could be a new point. You basically pass it into the sigmoid function using the weights and multiplying it with the dot product and adding the bias term. And so that will actually give us what it's predicted to be. And we'll do that for 2 different ones just to see. So we can see for the first one, it's predicted to be 0.2755. So since that's closer to 0 than 1, we would say this predicted class 0. And then oppositely, this is closer to 1. So this would be like predicting class 1. And so that's kind of, sure.
So the weights is random number, right?
Mm-hmm.
So, but in the model, we can see for a certain weight, the error is the minimum.
Oh, you mean like here?
No, go down.
Oh, I have to go back here.
Yeah, so the MSE, like around before 200.
Mm-hmm.
So that has specific weights, right?
Yeah.
But later on, when you do the prediction, the weights you chose is random. So that is not the best weight we got from the model, right?
Well, so the mean squared error is basically continuing to decrease. So like if we take the weights all the way at the end when the mean squared error is the lowest, that's going to be our best bet on the guess of the weights.
Yeah, but the weight is still a random number. How do we know?
It starts off as a random number, but then depending on the error that we get when it passes through the network, we adjust it a little bit either way.
Oh, right.
We either increase or decrease it slightly, depending on our learning rate.
Can you explain that part a little bit?
Sure. So that's basically in here. We're basically doing what we did with gradient descent, using the derivative of our sigmoid function and then both our error term. And it's multiplying that times our inputs and then times the learning rate. So that creates basically the step size, or how much to move the weights. And so this is like technically an array. It's like you know, 3 different values. So it's like 0.2, 0.1, minus 0.3. Because we have 3 different weights. So this is like an array of changes to those weights.
So we got a adjusted weight. Toward the end, our weight should be like optimum.
Right. We adjust it just a little bit, and then over time, it'll approach the optimum values.
Okay.
But you can see like this weight 1, like we started to make it lower, and eventually it ended up not being good for it to be lower, basically. So then it corrected and moved it back up towards a higher value.
And these weights are for our different terms, right?
Yeah, so these first 3 are the weights. So that's basically the coefficients for each of our inputs.
Matt, how did you set the learning rate? Like, what made you decide 0.5?
That's just kind of like a common one. Really anything from like 0.01 to 0.05. But really with larger neural networks, you'll see like much lower learning rates, like 0.0001 or even that. And actually what we'll end up using is kind of a dynamic learning rate through the use of an optimizer. So it'll basically adjust the learning rate over time. So it'll start off higher and then kind of go lower. But here it's kind of a simple case. It's just going to be static the whole time. Any other questions on this part before we move into the Keras stuff? There's a lot more in these videos. He has one that's a lot more technical and kind of math and calculus oriented. So if you're interested in kind of understanding that better, I'd recommend that. But yeah, so now we'll take a look at basically how to do this a lot easier with the Keras library. So you'll use this for basically any kind of neural network you'll use. It's built on TensorFlow as the backend, which TensorFlow is kind of a lower level library for neural networks and deep learning. Keras is kind of a higher level API. So it uses a lot of the TensorFlow stuff, but it makes it really easy to implement and kind of makes it more just like regular coding in Python. So to start off, we're going to have to import a couple libraries from there. So the first is sequential. This is basically our model. And then in Keras, the way you build the network is kind of by adding what's called layers. And so a hidden layer, just a normal one, is called a dense layer in Keras. So we'll need both of these imported. It might take a second. And yeah, you'll see using TensorFlow backend. And it's taking a while. There we go. All right. So in this next part, we're just going to make kind of a fake data set so that we can try out a neural network with Keras. So this will make a classification data set. We're going to have 2 classes, 1,000 features, 10,000 samples, and we're going to make it kind of difficult to separate the 2. So this would normally be a challenging data set for other machine learning models. So like random forest and stuff, we'll kind of compare it to one of those. But this will at least make the data for us to work with. And we're going to go ahead and do a train test split, just like usual. And then here, just so we have something to compare to, this will just be a random forest baseline, just fitted on our training data, and then we'll check the accuracy of our test data. This might take a second because it's a rather large data set. But while that's loading, we can start building our neural network. So this is kind of how it'll look each time. You'll start off by creating a model object, set it equal to a new instance of sequential, and then you'll kind of go down through and add each layer. So we're going to add our first layer here. This is hidden layer number 1. You'll notice this one has an input shape. Since it's the first layer, you have to pass in the input shape. And to determine the input shape, you kind of have to look at your data. In our case, we know we have 1,000 columns, 1,000 features. So each of our data points that we pass through is going to have a first shape of 1,000. So that's kind of where we get that. This first number here is the number of neurons in that hidden layer. So we're just going to choose 4. There's different guidelines on what values to pick. Usually you'll see something like 16 to like 64 or even 128. And then sometimes they'll like increase going to the second one and they'll like double it. So you'd go like, or square it or double it, I mean. So you go from like 4 to 8. You'll kind of see and understand that more when you start using them a lot, but there are some guidelines to pick that. It's not completely arbitrary, but in this case it's going to be because we're just messing around with it. But so we're just going to choose 4, and then we're going to have, yep.
So is it always going to be 1, 2, 4, 8, like the pattern of
That's
gigabytes
just,
and stuff?
it's not like a 100% thing. That's just what people have tended to do for some reason. Like you'll see like 30, like maybe 2 layers that are 32 and then to 64. Or you'll kind of see this like expanding and then contracting pattern. So it'll go out to that and then they'll actually bring it back down in.
Right, but does it have to be that, like, I forget what it's called. It's like a specific type of number set.
Oh, like powers of 2 basically.
Yeah.
No, it doesn't have to be.
So I could choose like 57.
Yeah, you could choose like a random number, like 3 or 103. I think just for it looking nice and symmetrical, they tend to do those values. So, so we'll stick with 4 though at first, and then we'll add a second hidden layer also with 4. And then you'll notice in here we have an activation, and you'll see this word ReLU. So I think on the next slide, okay, yep. So here's some activation functions. This is basically what they do with inputs that you give them. So you can see sigmoid will basically be between 0 and 1, like we've seen before. There's tangent, which will be from -1 to 1. Then there's ReLU. So if it's less than 1, it'll basically bump it up to 0. So anything less than 1 will just be 0. But if it's greater than 0, it can be any value basically. And this stands for rectified linear unit. ReLU is definitely the most popular for just regular dense layers. Sigmoid and tangent are usually more so for your outputs, because at least in binary classification, sigmoid is perfect because it's 0 to 1 between your 2 classes. There's also leaky ReLU, which is really similar to ReLU, except it allows a little bit of values that are less than 1. I haven't really seen this max out one or this one at the bottom too much. You'll almost always see ReLU or sigmoid or tangent on the last layer.
Hey Matt, the input shape of the first hidden layer, do we just put the input shape there? Do we just put the number of features there and we can keep the second item blank?
Yep, so at least for right now, if you're just gonna have like a flat list of inputs and features, then you just do it like this. So it's basically number of inputs, comma, and then just nothing is the second part. Because then we don't have to say how many we're passing in. So this could be any number. Like we could be passing in 500 or just 5, but by leaving that blank, it basically tells it we're gonna get 1,000 features and then we're gonna get X number of those samples.
Why you still keep the comma?
It's just kind of the syntax. Let me see if we run this, this will print out the summary. I guess it doesn't show the shape there, but this will show the output shape. Oh yeah, so that's what the none is. It's basically so that it's kind of a skeleton so that any number of samples could be passed in, if that makes sense.
Got it.
Yep, and then once you like have all your layers, you can run model.summary, and this will tell you a little bit about it, the names of the layers, the number of params. So this is basically how many tunable params there are. So since we have 1,000 different input features and then 4 dense layers, we get this 4004. And then it kind of shrinks that down. So in this layer, there's only 20 tunable params. And then to this last one, there's only 5.
Does
so
it mean
usually,
that we have 4,004 neurons?
I think that's because, let's see. I think it's one of those things where it's like indexing in Python, how like, 0 is the first position. So there's basically an additional one. So it's like there's 1,001. I think that might be why. But basically when you look at this, it'll usually kind of go down and decrease as you get towards the output. And usually it'll kind of expand first. So you'll start off with like a smaller number, increase to a lot of params, and then kind of dial it back.
I mean, what is the params? Like what?
So that's like,
model?
so our input is basically going to be, 1,000 neurons. Yeah. And then our first hidden layer is 4. So each line is a param.
Oh, I see. So the weights.
Yep.
Okay.
Yeah, so the weights. And then to the next layer, there's going to be 20. Oh, I think it's the bias terms. That's why. So each of these neurons has a bias, and that counts as a param. So you have the 4,000 weights and then the 4 bias terms. And then here you have the 16 weights and then 4 bias terms.
Okay, so is the weights plus the bias terms.
Mm-hmm. And then we'd have our output here, just 1. So you have the 4 weights and then 1 bias term. All right. So now we have the model architecture kind of set up. Now we have to do something called compiling it. This is where we tell it what our loss function is going to be, so what we're trying to minimize. So this is just kind of something you have to learn, but for binary classification, you almost always choose this loss function, binary cross entropy. It's basically set up to handle binary classification. And if you go on the Keras documentation, it kind of will show you a little bit more of how it actually works. But all you need to know for now is that this is what you choose for binary classification. Then we have the optimizer. This basically handles the learning rates and the adjustments to the weights and biases. And you have different options here. Atom is kind of like the go-to. There's a bunch more though. And basically what they do, Atom in particular is adaptive. So like I said, it'll start the learning rate off maybe kind of high, and then it'll kind of lower it over time, depending on the steps that we take in adjusting the weights and biases and then the errors that we end up getting. So it basically does that in a dynamic way instead of just having a static learning rate the whole time. And then you can also pass in metrics that you want to basically track. So each epoch that you train for, it'll check this for you. It doesn't train based on this. It'll just kind of keep track of it so that you can monitor the progress. And so we're interested in accuracy since we're doing classification. But you could pass anything in here. You could do like mean squared error if you're doing regression, or really anything else. You can actually make your own custom metrics too and pass those in. But for this, we're just going to do accuracy. And then lastly, this is training the model. So you call fit. And if you want to be able to kind of view the training history and have it saved, you need to save this as a variable. You can also run it without, but then you won't be able to go back and reference the changes throughout the training and kind of graph it, as we'll see in a second. But so for parameters for this, you pass in your X and then your Y. Then you pass in something called the batch size. So this is basically how many samples are put through the neural network at one time. So this is largely dependent on your computer and what it can handle. Usually you'll have values from like 16 to 256 is probably the highest. This also follows that like multiples of 4 or 2 or whatever. So this kind of depends on what kind of computer you have. If you have kind of a slower processor, you definitely want to keep it to like 16 or 32. If you have a better CPU, you can go up to 256 even. And then something we'll get into later, if you have a GPU, you can actually use a GPU with Keras, and your speed will be so much faster than using your CPU, like 10 times as fast. So we can definitely get into that later on, but for now using your CPU is fine, and most people should be able to do the 64. But so this is how many samples are loaded in at once and sent through the network. And then epochs, that's how many times the entire data set is passed through the network. So if we have we have 10,000 rows and our batch size is 64, we take 10,000 divided by 64, that's how many times per epoch our model will have data ran through it. So that's kind of the thing to keep in mind. The epoch is how many times the entire data set is passed through, and the batch size is how many samples are passed through at one time. And then verbose equal to 1 will basically spit out a line each time, telling us our accuracy and our loss. And then this last part, validation data, this is where you can pass in test data, and it will also spit out our metrics for that test data as well. So that can be useful because usually you're more concerned with how it's doing on the test data. So with all that, we'll go ahead and run this. And it'll kind of see what the output looks like. So we're training on 8,000 samples, validating on 2,000. It'll say the epoch number, and then it'll do this neat little animation. It goes through each batch, finishes the epoch, adjusts the weights, and then checks the metrics. So we can see here our accuracy started off at about 51.9. And after 10, it increased to 53.3. So not a whole lot of increase there. So we're actually going to tune this model a little bit and try and make it better. I guess before we do that, we could just take a look at these graphs. So this first one is accuracy of the train and the test. So we can see the train kept improving, but the test didn't really improve much. It kind of stayed the same. And then for the loss, both basically decreased, but then they leveled off and basically stopped decreasing. So one way to make the model better might be to add more nodes to these hidden layers. So we could go up to like 16 and 16, recompile it and fit it. All right, so now what were we at before? Let's see. So we went up to about 53. So now we started off at 51 and we went up to 61 on the test accuracy. So we did a little bit better. We basically gave it more weights, more parameters to tune so that it can better fit to the data. So we could probably increase this again to like 32 and get even better results. Yeah, so see, we're already at 61 after 4 epochs, then we're at 63 and 63 at the end. We could also increase the number of epochs, so we could go up to 25.
Matt?
Yeah.
Just maybe I missed this, but the last layer that has I guess a one node, is that just because it's a binary class? That's the output layer.
Yeah.
And so it's one because it's a binary classification, but if we had multiple classes, it would be however many classes.
Yeah, so if we had 3, then we probably want 3 nodes, but it's kind of a trick since we only have 2. We really only need to know if it's not one of them.
Okay.
So yeah.
But so if you did have 4 classes, you would have to have them the four
Yep.
nodes. Okay.
Mm-hmm. Well, maybe you could technically have 3, and then if it's no on all of those 3, then you know it's the 4th one. But almost always you'll just have 1 for each class you have. So, yep. All right, so let's see, after 25, we got all the way up to 70% accuracy. So that's pretty good. We can see our train is really high, so we're definitely still a little overfitted. But just by adjusting a couple numbers, we did see a big increase. So an important thing to look for is when a neural network kind of stalls. So if your accuracy or loss kind of stops changing, you want to stop training. Because if it's not changing and you keep training, you'll basically keep overfitting your data even more. So you kind of want to hit this sweet spot where you stop it right as it's starting to level off. So if we print out our graphs here, so yeah, so we can see at the very end, our loss didn't really change much. So we probably would have wanted to cut it off at like 18 epochs or something. And that might give us a little bit better results. And we could also go back. This is one of those things where like you could play around with it a million times. There is a grid search library for neural networks, but it will take so much time to run, way more time than grid search for like random forests and stuff, just because training takes so much longer. And so you usually don't want to do that. You usually kind of want to just try out a few different options and kind of keep the best one. So yeah, so we could go back and add actually more layers. Like we could go up to like 4. We could change these to like 64, but that's going to increase training time. So that's kind of always the battle with neural networks. You're kind of going to have to look at what kind of computer you have, how long it's going to take, those kinds of things. So that's kind of an example of using Keras. There's a lot more you can do. There's a lot more different types of layers, different cases where you use different loss functions and optimizers, but this is at least an introduction into it. And so then for the activity, we're going to build another network, and this is actually going to be using the MNIST dataset, which is basically a data set of really small images of hand-drawn digits of numbers. So this is kind of what they look like. They're 28 by 28 grids of grayscale numbers. And so there's basically 784 total pixels. Each of those is an input. So you basically have 784 inputs. And then your output are numbers from 0 to 9. So you have 10 different possible categories. So it's this really big network then, since we have so many inputs. But you'll see how neural networks can kind of rise to the task of this challenge despite the large feature space and also number of classes. So I kind of have some steps here to outline it. I know you're going to be a little bit in the dark since you haven't had too much experience using Keras before, but I'll kind of be in the rooms to help, and I have some like hints here to help you out. But you'll basically go down through the steps, you'll load in the data, explore it, then you'll do some pre-processing, then you'll build a model. It's going to be kind of arbitrary. I give you some guidelines on like batch size to choose and stuff, but that's all up to you. And then you'll kind of run it once, make some changes, run it again. And then at the end, I actually have a way for you to draw a number of your own and pass it into the network to see how it does. So if you're on Windows, you can use Paint. If you're on Mac, I'm not sure what the like basic program is there to draw a picture, but you basically just need to draw a digit, resize it to 28 by 28, and then save it somewhere you can access it through Python. And then this function here will basically turn it into grayscale and get it to be able to work the same way as the MNIST digits that we're training the model on. So that's kind of the challenge. Does anybody have any questions before we split into breakout rooms? Serena, were you able to download the material and everything so you have this activity?
Yeah, it's just the notebook for Intro to Neural Networks, right? Just
Yep. And then it's just at the bottom. All right,
Okay.
cool. Pause recording. Yeah, so that's actually a good point. That is a huge problem with neural networks. They're really difficult to replicate results. There are some like seeds you can set for Keras, and you can set it for NumPy, but sometimes that doesn't even work. There is a lot of randomness because basically, like you saw in our like from scratch example, the weights initially start off randomly. So depending on where they start, they could be close to the optimal spot or really far away. So you do tend to get different results each time. So you'll usually end up basically saving a model if you get really good results on it. And then you can send that to people and they can load it instead of them running it from scratch on their own.
Mm-hmm. And what about, I would imagine with loss functions too and gradient descent, you end up with local minimum and maximum as well, right?
Mm-hmm.
So you can just end up in a spot where your function won't optimize its loss function and to the actual real minimum. It will just end up stuck at a local minimum.
Yep, and that is another huge problem. There are things you can do for that, like tweaking the optimizer. Some of them have different parameters you can try changing. A lot of it is really like finding somebody who's done something similar and seeing what they used. So actually something I'm going to have you guys do in the coming weeks is read through some like academic papers that use neural networks. Because that's actually where you're going to find kind of the best examples of what to use for things is people who did similar things and what parameters and stuff they set. So, yep, good things to keep in mind though. All right, so who wants to share what they did?
I'm just waiting for everything to not be a 5.
Try using a thicker like marker or pen. I think sometimes if it's too thin, like just the default on Paint was giving me bad results, but then I thickened it and it made it better. Because you basically want it to be similar to how they look in the data set that you're training on. Ideally, you would have, you know, different thickness in the drawings, but this data set's kind of small, so they're all kind of similar. Did anybody have an accurate one that predicted their drawings pretty well?
One time.
One time. Anybody do better than one time?
How can you do prediction on like different pictures, like setup pictures?
So you could pass in like a list, you mean?
Oh, okay.
Yeah, so just like how you train on like a 10,000 or whatever, you could pass in a list to the predict and it would predict on all of them.
Got it.
All right, well, let's just have someone go over what they did at least, even if you didn't get the best model. So do I have someone to volunteer? Should I pick randomly?
I can go.
Okay.
Wants to. All right, here. Actually, wait, I may not be able to go. I'm sorry. I was having the security issues with my Mac. Oh, no. Is it working?
Mm-hmm.
Great. Yeah, so we ended up doing 3 hidden layers here with neurons of 4, 8, and 16. So the first thing that we did is after we explored the data and saw that it's the 28 by 28, we do the flatten so that the input shape is flat. And then from there, we have our 3 hidden layers, one of 4, one of 8, one of 16. And then we do our activation one, which is 10 neurons, and it's the softmax instead of the binary or categorical one. And then from there, we do our compile with the categorical cross entropy. For this one, we actually experimented with the optimizer as well and did Adamax instead of Atom. And our metrics, we're using our accuracy, and then we kept the epochs at 10. The reason we didn't really experiment much with the epochs was that every single time that we ran it, we typically found that by about the 7th or 8th epoch, our model usually leveled off pretty smoothly on accuracy. And so you can see here, when we ran that, we started with an accuracy of 0.57, saw immediate drastic improvement, and then leveled off in kind of the 0.865 region here. And we tweaked around with some other things. As I was talking about earlier, I tried 844. We tried going from big to small, small, big, small. We ultimately ended up going with this model, and it gave us pretty good results, but we never really got anything above kind of the 0.86, 0.87. We never got into cracking like a 0.91 or anything for accuracy. And so, yeah, that's what we ended up doing.
Cool. Thank you. So yeah, I think a couple of the other groups actually got like 95, 96% accuracy. So it really just depends on the number of layers and stuff you chose. I was going to show you my example here if it would load, because I did it just one time and got like 60% accuracy for the test. But then I actually was getting really good results on my drawings. So I'm thinking maybe when you're getting up to the 90%, it might be kind of overfitted to the training data, because your drawings are just going to end up looking different because they came from, you know, this other program. They got like kind of downsampled to like the right size and stuff. So that's probably why. You might try just only training for like 5 epochs or something, and see if you get a little bit better. Because yeah, let me share my screen real quick.
Matt, it's not necessary that the Y values are, they correspond to like the actual number, right?
Yeah, they'll correspond to the actual number because you have 0 as one of them. So let me see here.
And Matt, is it the more hidden layers, the better? Or how do we decide?
You
Layers?
usually want to do as many as you need. So you start off with like the lowest number, and then you kind of add. And then it's also dependent on your computer, like what you can handle, how much time you want to spend training, that kind of stuff. But usually more does mean better up to a certain point. So like here is mine, let's see. Okay, so no, actually I had about 97% accuracy, and this is one single layer, but with 128 neurons, batch size of 256, 10 epochs. And I drew it with like a thicker pen in paint. I think that maybe made a difference, but like it got the 3 correct. Let me see if I can
Matt, so you're saying when you one-hot encode, the picture with 0 is going to correspond to the category 0, the categorical value 0, and
yeah.
so on.
Yep.
Interesting.
It's funny that I draw a 7, but it gave me a 3.
Those aren't very close. Some of them make sense, you know, if it's like a 6 and a 0 or something.
Yeah.
I'm trying to draw another one real quick.
Draw 4.
I did, actually. All right, so I think it's test2.png. Yeah. So I got that one.
Nice.
I really think it's the thicker.
But your model is better. It's like a 97%.
Yeah, I guess that's a little bit better. But I wonder if I could do this for like 5 and get the same results. Let's see.
Mine is 96.96.
Try increasing your batch size maybe.
Okay.
So yeah, I got it after only 5. Let's try 1 epoch. Okay, so with 1 it gets it wrong, but I mean 5, that's pretty good. Yeah, it's really just something you have to mess around with. Try to find a sweet spot.
Is there a way to kind of know roughly where to start?
Where to start for what? Like number of things?
Yeah.
Like you can find guidelines. Usually the default is like 2 layers of 32 each on something simple. It really just depends what you're working with. But usually the larger your input size, so here we have, 784, that's a lot. So you're gonna want a lot of neurons to kind of give that weights to connect to. But if we had like only, 50 inputs, then we would want like a smaller number of neurons on our layers. Okay. So like it kind of depends on your input shape.
Okay. Yeah, that makes sense.
But yeah, that's all I have for tonight. This is definitely just the start. We're going to have at least 2 more study groups working with this kind of stuff, probably more. And there's a good chance you'll use this in your capstone in some way. So definitely start familiarizing yourself with it. You'll want to look through the Keras documentation when you can. There's a lot there. So just kind of familiarizing yourself, and over time you'll learn it and learn the tricks of the trade.
Nice.